Thank you very much, Shawn. Today we are going to talk about machine learning, and you have more information on what this video is going to, or what we are going to do in this video. So let's have a look.
Yeah, absolutely. Thank you, Robert. My name is Shawn Hymel. I'm a developer relations engineer from Edge Impulse. And I want to talk about machine learning, as Robert mentioned, what this means, and specifically not just machine learning, right? We're in this big AI, everyone knows about ChatGPT. Like there's this huge hype around machine learning right now. But I want to focus on taking machine learning and applying it to embedded devices, and specifically running machine learning, deep learning neural networks on an embedded system. And I'm going to do that using an Arduino because that's easy to do, but it's a ARM M4. It's a fairly low power microcontroller, and we're going to be doing image classification using supervised learning. So machine learning is generally categorized into three different divisions. So you have unsupervised learning, where it essentially tries to group patterns of data together to look for patterns. In the sense of, I might have, marketing uses this a lot, where I have people interacting or buying certain products and I don't know anything about them. Can I group all of that together and look for patterns there to be like, these people cluster together and these people cluster together. So maybe we target them with these ads, and these are certain groups and personas. So that's unsupervised learning. Supervised learning is exactly what we were talking about. The thing that you mentioned is you have all of this data coming in where I have known good labeled samples. In this case, I'm going to be taking pictures of rock, paper, scissors, and those are labeled, and those are going to be my training samples. I'm going to label them manually so that the computer can learn, like, this is the image of me giving the rock symbol. Therefore, I need to create a model that tries to predict this. So the idea behind a machine learning model is I want to create an arbitrary mathematical function, right? This all just comes down to, I'm going to say basic math, but there's some calculus involved, especially when it comes to training. But I want to create an arbitrary function that, when given an input data, it tries to predict that label. And the idea is that label should be the same as the label I was given, also known as the ground truth label. And then you use something called training. And a lot of times we use there's lots of different methods here. When it comes to neural networks and deep learning, which is the popular thing right now, that's usually backpropagation and gradient descent. And you update the parameters, right? Think like your coefficients or your constants within that arbitrary mathematical function. It looks at the output, figures out how far away that predicted output is from that ground truth label. So that's where you get that loss function that you see down at the bottom there. L, the loss function of the difference, is the difference between the ground truth label and your predicted output. And it uses that loss function to update the parameters in the model so that the next time through, the model gets a little better at predicting based on that input and trying to get closer to that ground truth label. Once we have that model and it works well enough within our constraints, we can then use it in something known as inference. This is where we take that model and we give it unlabeled data it's never seen before, right? I give it a new hand symbol. It's never seen this before. And it tries to predict. It sends those array of numbers through this arbitrary mathematical function, and it predicts that output, right? It goes, I think that's rock based on all the other pictures you gave me previously. And I have this function. I think you're giving me the rock symbol. And the idea is, it should work, right? But this is all probability. We can't guarantee, even if the function itself is deterministic, a lot of times that input is not deterministic. So we often have to look at larger sets of data to say, this is 80% accurate or 90% accurate. And I find that 90% accurate is good enough for like workshops, courses, sometimes even academic papers. 90% is really good. When you start getting into production, your Alexa, it needs to respond with like 99.99999% accuracy, or it really irritates the users, or it misses stuff. It doesn't hear you correctly, whatever it might be. You got to have super high accuracy for a lot of this.
I have a question. So I understand that you have to somehow create this model fx function, but what I never understood is how you create these functions.
So there's actually a lot of different ways to create this function. I'll show you neural networks, which is this really popular way right now. I'm not going to get into the math behind gradient descent because that's like several lectures worth of college course material. It's fascinating. There's some good courses out there you can take. It's really good if you like try it by hand. You have to like solve a gradient and all this stuff. But support vector machines have its own way of updating the model. What are some other like decision trees? They all have their own way of updating this model, and every algorithm's a little different. So it's really like you go read these computer science papers and they like list out, here's the algorithm for updating your models. And it just shows you how to tweak those parameters based on your input data and output data.
Is there a way, maybe somehow, how we could imagine this model? Because sometimes I imagine it like some kind of space where a computer will put some points, and group of the points will be like, I don't know, this is paper, yeah? Or if somewhere else there is group of points, which is, I don't know, scissors. And when this X input will end up in the point close to this specific group, that's when it will decide, okay, it looks like it's going to be paper, for example. But I think I read it's not like three-dimensional space. It will be like multi-dimensional.
Yeah. So you're thinking of probably the nearest neighbor, right? Where your inputs, you think 3 dimensions, which is easy for humans to conceptualize, but it might be hundreds or thousands of dimensions. When we talk about these images, they're like hundreds or thousands of dimensions, because each value in a pixel is its own dimension. So that's a good way to think about it, is what you're describing is nearest neighbor, usually like k nearest neighbor or something like that, where you have the groupings and you say like, oh, I see a new point. Is it closer to this grouping or to this grouping? And that just provides the label. Like we've had a grouping over here. This label comes in. We've labeled this grouping for something like supervised, and we say, oh, this point in space is close to this grouping. Therefore, it is part of this label. That is a very common way to do it. Training for nearest neighbors is very easy, but inference is very hard because you have to regroup the groupings every time, which means that the inference side is actually very computationally expensive.
Okay, so there are much better ways how this model works, and I can't really imagine it. It's just mathematics or something. Yeah.
For real simple, I like to think of like a neural network as like a big filter, right? And the how stuff goes in is important, but you take a bunch of input data, which is all these dimensions, and it goes into this, I think, physical filter, and it drops out this one little label, like a little ticket, like, oh, I think this is it.
Okay.
Right. So that's how I imagine it. But you're absolutely right. It is a lot of times it's where are these things grouped together in space, and there's just different algorithms to do that. But then you get into things like, oh, even though this is over here, like you can divide up the groups nicely. But what happens when they're not very nicely divided, right? You don't have a linear separation among the groups. And that's where a lot of these support vector machines and neural networks come into play, is it helps you with nonlinear separation.
Okay. Because I had no idea how it actually looks.
Yeah, it's pretty wild.
But we don't need to understand completely how it works, and we can still use it, correct?
Oh, yeah, absolutely. In fact, neural networks have a problem in that a lot of times they're black boxes. And so if you often hear the idea of like explainability being thrown around, because they are so complex, even the most brilliant mathematicians can't fully wrap their heads around what are going on with some of these larger neural networks. And so they're just treated like black boxes. And there's all these tools to help you train them, tweak them, tune them, deploy them. So you can just treat it as a black box. And it helps to know a little bit about it if you want to kind of tweak the architecture yourself. But there's known good ones out there like AlexNet, MobileNet, all of these. You can just pull off the shelf, put my own images in, it trains, and I just deploy. And I'm like, I don't know what's going on in AlexNet, but I can use it.
Okay.
Absolutely, you can treat them as black boxes.
Okay. And then there are some parameters. We will talk probably about some of the parameters which we may change or which will influence the result, correct?
Yeah, so I can talk a little bit. So there's parameters. Generally, when you talk machine learning, there's parameters that are automatically updated. So we call those the parameters inside the model. There's other things called hyperparameters, which are the little levers you can pull, right? How many nodes in this layer? How many layers? How do I start the parameters? How many training cycles do I go through? Those are known as hyperparameters because generally those are things that I tweak as the designer. Or you can have like what they call auto ML, where I've got other machine learning algorithms or other algorithms that try different parameters, train the model, see how accurate it is, try different parameters, and I can set up all these training loops and experiments, and then there's all these tools out there to help you do that, to help get the best model for your application.
Okay, so basically these parameters can make, I don't know, computation longer, but I don't know, more accurate, or they can, I don't know what else they can.
Well, generally, yes. Like the bigger and more complex your model, usually speaking, means it's going to be more accurate. You run into a problem called overfitting, where it might be so accurate that it like perfectly predicts your training set, and then you try to throw a test thing at it that it's never seen before, and it just doesn't know what to do it because it perfectly fit to your training set. So that's called overfitting. But usually, and the more complex models means more accurate. It often means you need more training data in order to get them to be more accurate. That's, it can do inference in other situations and still maintain that accuracy. But as a computer person yourself, the more complexity, the more computational power that you need, the more memory that you need. So especially in embedded systems, it's a trade-off. I have to very carefully pick a use case where this is going to work well for, and then pick the model for that use case. So a lot of times it's really bounding your problem, right? Think like your Alexa. That initial keyword, that Alexa or Hey Siri, it's not trying to understand all the English words. All it's doing is just looking for a very particular set of syllables. And so it's a very narrow bounded problem. And that way it can respond very quickly in order to get that information out and then open up that microphone to start streaming to a much bigger model on the back end that then can understand what you're trying to say, intent analysis, and all of that.
Okay, I understand. So these parameters will help us to be efficient in specific situations which we need. Like we need to be efficient very quickly for the Alexa word, but the other situation, understanding whole sentence, maybe it doesn't have to be so efficient, but it has to be more accurate. And tweaking these parameters will help us to work between these different situations.
Correct. Yeah, it's all a trade-off. Consider what you need to do, how accurate you need to be, how complex, how much kind of computational or computational power that you have. All of that's very important to consider going into this.
Okay. What else you have here?
Yeah. So I hope that the one I didn't mention was reinforcement learning. It uses a little bit of supervised learning, but that's the idea of it tries things on its own and then learns over time how to do something. So you see like Mario, like a AI agent playing Mario or Atari games. That's all reinforcement learning. That's actually something I'm working on right now as in my own personal time, because it's really cool, but it's different than supervised and unsupervised. So that's the third one I didn't mention.
Okay,
so the other one I wanted.
That's interesting.
Yeah. There was a paper last year that started talking about it's been done in robotics, but there was one last year that's like connecting it up to like it's a OpenAI gym, or I guess it's now Gymnasium. Somebody else like took over that project, but connecting hardware up. So think like I can plug in an Arduino to Gymnasium and it like learns to balance on its own. I'm like, that's so cool. So this is, fairly recent kind of stuff that people are working on it, but reinforcement learning, just like supervised learning, has been around for a while.
So how do you then tell this, in this situation, what is right and what is not? You just set some kind of boundaries and it knows once it crosses the boundaries, it automatically decides it failed?
So you have to set that up. So you set it up. It's usually done through rewards. And so you say, oh, if I go out of bounds, maybe that's minus 100 points in your reward. Or if I balance correctly and the longer I do it, you get plus points, every second or whatever it might be. Or like think Mario, like, oh, if your character dies in Mario, then that's minus 100 points. But if you make it to the end of the level, that's plus 100 points. So now it tries a whole bunch of different things. So you've probably heard of like explore versus exploit. So initially the idea is it tries to explore lots of different things, like, oh, I can jump and move, so let's try all these things, but I died at this point, so let's try something new this time. And it slowly learns that over time. So it's kind of supervised, but it's not the sense of like, oh, here's the ground truth label. It's you have to figure out how to do that, and I'll kind of reward you along the way. So as the creator, the engineer, you get to figure out what algorithms to use and how to reward the agent based on its actions.
How does it decide what it is going to try? Is it like initially, randomly, or?
Usually randomly. Usually
Okay.
it's completely random because it has no idea about the world. You can tweak some of that if you want to like reward certain actions, but generally the algorithms are, I'm going to start by just trying random stuff and then figuring out what works from there. But just like in other machine learning, you can often end up in like a local maximum usually they're like they try to maximize rewards rather than minimize losses, so they call it local maximum, and it will do something very silly and unexpected, but it's like, oh, I found the easiest way to get maximal points with
But it's
least
not what
amount
you
of
wanted.
effort. Yeah, and you're like, that's not what I want. So you have to go back as the designer, and you're like, okay, I'm gonna penalize you for doing that, or I'm gonna give you more reward in the future so you can try to get there for the more reward. Or you can do reward shaping where it's like, I'm gonna give you small rewards along the way based on some of your actions. So that you can try to figure this out. So like I'm helping you as like a teacher is the idea.
Okay, interesting. I have no idea how I would do that, but
I'm slowly learning it. I took a course on it. It is, oh man, if you thought like regular machine learning, like supervised learning was hard, this is like next level stuff.
okay. What do you have here? This is
So
very
this is
curious.
getting, yeah, we talked about the idea of like we briefly mentioned, why do we care about doing embedded machine learning? And I think I mentioned like the Alexa thing, the smart speaker, and there's a number of reasons why you care to run it on embedded systems. We usually think machine learning is these, big, massive, complex algorithms running on these big servers. Most machine learning these days, I want to say like 90+% machine learning these days are like run on servers. You create an endpoint, and I feed it data, right? Think like Chat GPT, whatever. What was the OpenAI one that was super popular where people were like prompt and it would generate a picture? I can't remember the name of that. Everything's Chat GPT right
Mid
now, but
Journey or something like,
yeah, one of
or
those, right? I give it a prompt and it gives
Dali
you
or
a Dolly, that's
yeah.
it, Dolly 2. So that was the one where you like give it a prompt and it made these amazing pictures. So those are all running on massive servers, and that's what gets a lot of attention. But what you don't see a lot of times is people talking about like, hey, how does your Alexa work, right? Like, oh, it just streams to the internet. Like, no, there's actually some local machine learning going on. So even like your smartwatch could have local machine learning going on where it's doing simple keyword spotting. It's just looking for that one phrase, a couple of syllables, and the algorithm is, the machine learning model is very finely tuned. It's a smaller model. It's tuned to just pick out those phrases. Now, this does mean your microphone's running all the time, and it's recording, maybe a second or so of data in order to do this keyword spotting, which is why I usually turn it off on like my phone, because I know it's draining the batteries to do this all the time. But what's really cool is we're now getting to specialized hardware to do this kinds of things. So like a Hymel, Sentient, the new ARM, what is the ARM U55?
I don't know.
These are all like very specially designed to run these algorithms, and sometimes it can be done in hardware. I've seen FPGA designs where it's a neural network in hardware, and you just update the parameters, and it will figure stuff out in a few clock cycles. Super efficient, but highly specialized. Or you can run it on general purpose processors, and you can take advantage of some like the DSP functions where you can like do multiply and accumulates, or some of these even like ARM Cortex M7s, I think maybe some of the M4s. They have single instruction multiple data, so SIMD operation. So like a tiny, think like minuscule graphics card where it can do matrix math fairly quickly, and that
So
helps a
that's what they
lot in
need.
machine learning.
For example, support for matrix calculations and this kind of.
Yes.
Okay.
So think about when you're talking about the multiple dimensions, a lot of times it's doing the same operation across multiple dimensions. So matrix algebra is massively important, which is why you see graphics cards getting used a lot for machine learning, right? A lot of these servers, they're graphics card farms because it's a lot of matrix multiplications, matrix additions.
Okay, so that's why standard microcontroller may not be the best, but the microcontroller which already has support for this machine learning, it has this kind of special arithmetical unit or something which has this which has support to do this kind of arithmetic which is used inside of the model to find out. Yeah.
Correct.
Okay.
Yeah, so the basic, single instruction, single clock cycle kind of thing, or whatever your pipeline set up to be, not super efficient, but can be done. It's always a question: do you have enough memory, RAM and ROM, and how long can inference take? Right? If inference can take a second because you're doing stuff over long stretches of time, that's fine. There's nothing wrong with that as long as it's meeting your needs. But if a user wants, "Hey Siri" to respond in a millisecond, right? You're going to have to either make your model smaller, you're going to have to use specialized hardware, right? It's always a trade-off for these things.
Okay. Okay, I understand.
Yeah. So other things we're seeing are things like wearables. Here's an example of a plug into a shoe or a little battery powered thing, and it looks at your gait and it tries to give you feedback. Maybe if it's Bluetooth connected to your phone. And this was something for football/soccer where it could identify the actions that you're doing. It's using supervised learning to say, oh, you're kicking now, or you're passing, or you're dribbling, whatever it might be. And ideally it can give you feedback, right? You're like, oh, actually you should be doing it like this, like, oh, you turned your foot a little, a little incorrectly to pass. And so with the help of machine learning, we can get that kind of sports performance out of it, but also things like EKG, EEG. We can do things like using machine learning with electrodes around our head. We can start identifying brain waves, or maybe it's identifying anxiety attacks. Yeah. Well, what was the article I just read? They're starting to like reconstruct images based on people's like brainwave patterns, which is completely bonkers. I look forward. Wait, maybe I don't look forward to people seeing what I'm actually dreaming. That's not a good idea. Maybe that scares me more than ChatGPT. So, but things like my smartwatch, right? It knows when I had a nasty fall. That may be not machine learning. That may be just, oh, I saw acceleration over a certain amount,
Yeah.
or deceleration over a certain amount, right?
But
you
even
could do.
if you are looking at the watch, or yeah, it can be also done without machine learning.
Yeah, some of these, I feel like some of these things are like, oh, we're using machine learning. I'm like, you probably don't need machine learning from that. Like, you could just do like an FFT, and if you see a frequency spike in this range, right, there's a problem. You probably don't need machine learning, but like general anomaly detection, you can use machine learning. It likely won't be neural networks, but right, that's machine learning of like, oh, I see a grouping and this thing's outside my grouping. That's a problem. What you're talking about, like, let's have a cluster, right? Like, plot all of your things. Think accelerometer data over the course of a second. I can plot those in like 100 dimensions, and I see something outside of this, right? That's a problem. That's an anomaly. That's technically machine learning. Also, regression is now machine learning. Like just line fitting.
Yeah.
So all of those are machine learning. So you can slap your big, oh, we do AI on top of your product now if you do like regression or simple anomaly detection. So there you go. If you want to join the hype, right? If you do regression, you can say you do machine learning because it's learning from experience. But the other thing is like, think about like your watch. Like, you can monitor your pulse rate over time. Other, like maybe galvanic skin response and some other things. I don't know what they monitor these days, but like
Oxygen.
You can look at O2 levels. There you go. So it can look at all of those, and maybe it's like, hey, you're about to have a panic attack or something. It can identify certain patterns. Sleep tracking, a lot of that's done with machine learning to identify how my body changes when I fall asleep, and it can identify different stages of sleep just based on that. That's all done with machine learning.
I actually read something that some of these machine learning results may be even better than if a real doctor check you. And so
don't
maybe
don't
in
let doctors know
future,
that.
I don't know. But
Yeah,
I can
exactly.
imagine it really does work, because it can learn from so many data. No real person can actually do that.
Yeah. You have to think about, a lot of times doctors are just following these flow charts. Maybe they studied it, maybe they can identify certain symptoms. And a lot of times they go to these flow charts and they say, oh, here are the symptoms I'm seeing. It's probably this. Do these tests. And then you try to filter it out. And like, some of that can just be automated with machine learning, right? I still want to have a doctor with good bedside table, but I think like probably nurses could pick up a lot of this for them, and then they could run the test, because it's just machine learning making the actual decisions. But at least for now, I feel comfortable having a doctor like verify those results. Just like I don't trust everything I get out of ChatGPT. We're not quite there yet. I don't fully trust it yet, even as somebody who works in this field.
Yeah, I understand.
But yeah, I think it's I expect to find a time when cars are going to be safer. What's interesting is that for a while with self-driving cars, we are going to be more critical of crashes with self-driving cars until they're like 3 times safer than humans. Not just like a little safer than humans, but like some obnoxiously large amount, like an order of magnitude more safer than humans. That's when people will be like, oh, I trust them now, right? Which is super interesting that we somehow trust humans more implicitly. So it's just something interesting to think about. Even like mathematically, it's shown that yes, they're safer than humans. Or like, right, the same thing with doctors. Like, I still feel better having a doctor verify the results, right? But even if a machine, like you're saying, even if a machine's actually better at identifying certain diagnoses.
I don't know if they are better, but I think they may have much more information because a doctor maybe seen, let's say, 10,000 people in his whole life, but a machine can check millions of people.
Yeah. Yep, exactly. Yeah, it's scalable. It can also have like a wider range of inputs. Like even a general practitioner just can't specialize in anything.
Exactly.
But right, you could feed it to a machine that like has the specializations automatically.
Where we are going.
Yeah, I know we were promised flying cars and this is what we get.
Exactly.
We have the internet and AI. Turns out Terminator's closer to the truth than like Back to the Future.
Okay, let's go on the next.
Sure.
Slide.
So here's a bit of a specific example. So I'm going to show a vision example where, I'm going to show hand signals. But imagine a camera that maybe you just want to do person counting. So have you been in one of those offices with those like PIR sensors, and like if you sit there for a little while, the lights go out and you have to like jump and wave in front of the PIR sensor.
Toilets.
They're awful. Yeah. So one idea is like, oh, what if we have really inexpensive cameras that can see into a room and do people counting? And then not only can you like keep the lights on, you can also say, oh, let me adjust the HVAC because I know there's more people in this room, which is generating more heat. And so I can direct stuff into this room. Or like, not just an office room, this example, like an office room, but think like a convention center, right? I want to be able to quickly count hundreds or thousands of people to know how to adjust or scale up my HVAC processing, or I'm going to say like how much air to dump into an area or even an area of like a large conference room. So people counting is really important for a lot of these smart HVAC systems. And it can be done pretty simply with inexpensive cameras these days. But we think of AI, I gave the example of like, we think of AI as like, oh, we pipe the stuff across the internet, these giant servers somewhere, black box, and gives me some results back. So what would that look like if I said had 30 cameras in an office building? And let's just, for the sake of argument, say I need 240 by 240 pixels to do basic people counting in each office. And I'm going to say 8 bits per pixel. Let's keep it simple, grayscale. And I only need 1 frame a second, right? I only need to update the smart HVAC with the number of people in each room, no more than once per second. So a frame a second's fine. It just takes a picture, sends it off. What does this look like to your network? That is a constant stream of over like 13.5 megabits per second, which doesn't seem like a lot. Start expanding that out and you start hosing your network pretty hard. So for like basic IoT stuff, real basic, like 240 by 240 grayscale is not a big picture. But when we start scaling IoT, that's a lot of your bandwidth that you're hosing. So what if we did that processing on the camera itself, right? Mm-hmm. This is an OpenMV. These are pretty inexpensive. And rather than streaming all that data and hogging up your bandwidth, all it does is do person counting. That's all, like very, very narrow. Like it just needs to do a very simple algorithm of identifying number of people in a room, right? Turns out object detection is not super easy, but we're getting better at it. And like Edge Impulse's FOMO can easily run on this device. So I could do people counting pretty easily on this device now. So all it needs to do is just 1 frame a second, or excuse me, once per second, just say, hey, is there a person or not? And for now, I'm ignoring all the overhead that goes into like TCP IP. But the raw data, now it's just 30 bits per second, assuming 30 cameras, right? So not only are we saving on bandwidth by pushing that decision-making down to the IoT devices, now I have security. Now I can say, no, these cameras aren't recording you beyond whatever's on the camera memory for that blip to do person counting. You still have to prove this in like court of law or whatever.
Same
that
with
you're not
Alexa
really
and mobile phone or smartphone. Yeah, no one believes.
Yeah, no one's gonna believe you, but it's like the idea is there, right? You can demonstrate some sort of privacy, like no, across like it's not streaming your data, it's not storing your data, it really is just doing person counting. So in court of law, yeah, you could break down the code and show that, but the concept is there that I could have security. And then of course, like think battery powered, right? If I want to strap something to a tree and count the number of tigers that walk by for conservation efforts, I could absolutely do that. And now I don't have to worry about an internet connection to do the machine learning part for me.
Yeah,
right?
I understand
can be done
this.
locally.
So that's why it is useful to be able to do some of the machine learning directly on the chips and on hardware.
Correct. Is it the end all for machine learning? No, of course not. But certain applications, it makes a lot of sense to push it to these IoT devices, to these microcontrollers, and let them handle it. Especially with this new efficient hardware coming out that just like does it for us with like little energy use.
I'm actually surprised there are so many chips now which support this.
Yep. ARM's pushing it. Kind of neuromorphic processing is kind of a dark horse. I want to play with that. It's like spiking neural networks, which is like not like regular dense neural networks at all. It uses like differential equations to do the spiking. It's close to how your brain works, but it's supposedly super efficient. So I'm excited to BrainChip has one. I'm excited to like play with one if I can get my hands on one.
Okay, what do you have next?
All right. I'm gonna collect some data first, then we can come back to kind of how we're going here.
Okay.
But just broad overview of what we're going to be collecting. How does a digital camera work, right? So light enters these lenses, it shapes the light, all that light falls on an image sensor, usually something like a microcontroller collects that, and these are stored in just giant arrays for red, green, blue images, maybe an alpha channel. It's just a big array of numbers. That's it. Usually each one's between like 0 and 255, depending on your bit depth. We're going to be collecting stuff in grayscale, so it's just going to be one array that's each pixel is between 0 and 255. That's it. It's just a big array. Numbers. So I'm going to fire this up. So I've got my Arduino here. I believe that is for later. So I'm going to go to data capture. And I'm going to load this up. I'm going to start the upload, and then I can switch my camera here.
So what kind of Arduino do you have? Nano
Sure,
BLE. I have same.
Yes, very good, actually. I actually really like this board. It's kind of a catch-all. It's got all these sensors on it. It's fairly powerful.
Can we find it in browser so everyone knows what kind of board we have on the table? You will show it on camera, but if someone would like to play with this board, they can find it.
Yeah, absolutely. Before I forget, while that's uploading. So in the Edge Impulse GitHub repository space, there's this workshop Arduino TinyML Rochambeau. This is an exact walkthrough of what we're going to be doing right now. So, I mean, it is a full walkthrough. I'm actually going to be doing like half of this. So I recommend doing this, and there should be a link in here to that required. Oh, so this is the actual hardware that's needed. It's the Arduino Tiny Machine Learning Kit. It's the Nano 33 BLE Sense. There we go. But it happens to have this camera, which is like the OV7675. So you could always get that camera and connect it up manually, but this kit honestly just makes it easier. So this is the kit I recommend for doing this.
Okay.
But it is like here's two links for the Nano 33 BLE Sense. It's this board, and then here's the camera. So if you get those two things, you can hook them up. And I'm gonna switch over.
Okay.
All right. Yeah. Perfect. So here's a close up of the board. So yeah, we have the microcontroller here. It's got a bunch of sensors on it. That Nordic, what is it? The NRF 52840. There's the camera, and that's all we're going to be really using for this. And so now that you've seen that, I'm actually going to zoom it out because you're going to have to see my hand going above it. What we're going to be doing, I'm going to be doing my hand gestures up here.
Okay. So now the software, what you uploaded, what this software is doing?
So this software, all it's doing is capturing a frame from the camera. So I'm going to be doing my hand gestures up here. And then it's going to pipe it out over serial. So it converts it to RGB 888, probably not even needed because I think I'm just supporting grayscale. Where is it? So here's where it actually reads from the camera. We scale the image down because I don't need the full, whatever it is, like 320 by 240. I actually only need like 30 pixels by 30 pixels for this to work. And then it's going to case grayscale. It's going to convert it into base 64. And then it's going to send that out over the serial terminal. And then
so it is just, I don't know how many numbers in one row, basically.
Right. So it looks like this. So I don't fully remember. Let's see. Like what
It's
are we
not even
printing out
numbers.
here? No, it's all base 64. So it's like the same encoding you'd find on like a web page URL.
Ah, okay.
So I believe it is 30 by 30.
Mm-hmm.
And so it's converted to this base 64. So it's a little easier to transmit over a USB line.
Okay.
And then I'm going to kill my serial monitor here. And then what I want to do.
Ah, okay. I see. There is directory like 01 data capture. That's what we are using now.
Right.
That's the first step.
So we've uploaded that. We've uploaded the firmware to the Arduino. And so all it's doing is just capturing and spitting stuff out over serial. Forget how to use my venv here. Bin activate. And then now this has like all the Python packages installed. I've discovered that Python does not play nicely on macOS, and I've like created myself into dependency hell, and packages just stopped working. So I've been trying to get better about using virtual environments. So I made this little Python program. So we're going to fire this up over here, and I'm going to connect it to my Arduino that's on this serial port. I'm going to connect here. Should be connected. Hopefully it starts getting some images over here, assuming this all works.
So based on the data which you are sending through serial port, you will be able to reconstruct the image, what the camera is seeing?
Yeah, that's the idea. It reconverts that base 64 into an image. Let me try turning off my board and turning it back on. Give this like one more shot. So I'm going to turn this on. I'm going to connect. There it goes.
Yeah.
All right. So can you kind of see what's going on over here? So I put my hand over this. You can see my like 2 frames per second, but kind of all we need.
Okay. So in this picture, we are decoding the data which Arduino is sending through the serial port. So it is just to double check what we are actually sending through the data.
Yeah, because if you just said like put your hand up here, I would not know what the Arduino is seeing. So you can see on my webcam here, I've got the Arduino. I put my hand up here, and then my hand shows up here. But without that feedback, I would not be able to tell you where my hand is. So for the purposes of collecting data, this is very helpful. So I'm going to start, and I'm going to get my hand in position here. And what you'll notice, I'm not going to change my background because that would require a lot more data for this to work in different backgrounds. So for now, I'm just going to save, I don't know, a bunch of images of me giving the rock symbol. And you can see me moving my hand around. That's to try to create this robust model that can identify my hand in various positions. If it only had the hand in one position, it would only look for the hand in that position. And then otherwise, it's going to try to assume it's something else. So I got a bunch for rock.
And you just keep clicking on save image, yeah?
Yeah, you can actually see them down here where it's saving,
I see,
it's the label dot some hash and then dot PNG. So I'm going to do the same for paper. I'm going to move my hand around a whole bunch so it kind of knows what to look for. And
theoretically, this data, they don't need to be image. They can be even, I don't know, waveforms or sound form or something, sound file.
Correct. So like doing keyword spotting, it can be set like it would be just me recording my voice or recording a bunch of people's voices. The images are just nice to conceptualize. I like this demo because it's easy to like kind of visualize what's going on. But yeah, absolutely, you're correct. If you're doing keyword spotting, yeah, you'd collect a bunch of different sound samples, both of your target word and not your target word. So all the other words basically, and there's some data sets to help you get started doing that. So the other thing I like to do is collect background, because that's your hand is not present, and then also do unknown. So a lot of these are going to look the same. You were going to ask something. Sorry.
I just wanted to say I'm curious what is going to happen in the next step, because I would like to see how these specific data are going to be converted to something what the machine learning is going to learn from, or I don't know.
Right. So the other thing is, rock, paper, scissors are kind of my target. And so now I'm doing things that are neither rock nor paper nor scissors, but it's still my hand in the frame. So that kind of helps me create a balanced data set where I have close to a number of the same number of images among my classes is the basic idea.
Do you calculate how many images you created for everyone?
No, this is a total guess. Like the closer they are to being the same number, generally the better, but they don't, as long as you don't have like orders of magnitude differences is what I have found.
Okay.
So we're going to.
And the Python script which you started, it is also included in the Git repository?
Say that again?
The Python script which you use for this serial image capture, or I don't know how you do that, because in the Git repository, okay. If you go inside of the, yeah, exactly, show it, because I would like to see.
Sure. So that script is here.
Okay.
It's the serial image capture script.
Okay.
And once again, I'm not sure why it's not working on the M1s, but it looked like it had to restart the board.
Okay. So this one will open this small image where you can see the
correct, and then collect all that data.
Okay.
Yes. So the next thing I'm going to do it through Edge Impulse. I happen to know it well. It's a nice visual tool, but you could do this with TensorFlow. That would just also take a lot longer. So in here, I'll create my new project. I'm going to call it RPS for rock, paper, scissors.
Okay.
And then in here, I'm going to upload my data.
So is it important to upload only pictures, or you can upload also, I don't know, audio files or something else?
You can upload. Edge Impulse takes a variety of different files, including pictures, waveforms, whatever. You want them to all be the same, right? Because you're trying to work with the same sensor, the same data. That part's important. You can also upload like CSV files, so it can be
I see. Okay, arbitrary. I see it in the first line. Yeah,
right. Yeah, it can be arbitrary. So CSV, a lot of stuff that's like accelerometer data I do with CSV. I'm going to have it automatically split between training and testing. It's really a good idea to take about 80% of your data set, use that for training, and keep 20% aside. So then you get an idea, is your model overfit? Is it going to work when I put it to the field? Because that 20%, ideally, the model has never seen before. And then so we can see how it will work on that new data. And because I labeled my files with the label dot something, this is what this means. It's just I labeled that data to work nicely with Edge Impulse. But obviously, if you're doing this yourself with TensorFlow, no, I'm not building object detection. If you're doing it yourself with something like TensorFlow or PyTorch, you kind of have control over how you want to read in your data. Often they usually use things like NumPy, to where you just work with matrices in order to make this happen, and then you store everything in these like big NumPy arrays for training.
You can switch on your camera back, I think, now.
Okay. There we go.
You're back.
All right. So now we've got the data inside of my system. And so now it's set up to be used as training data. And so you can look through here. Here's all the different rock versions. Let me make sure that my labels are correct. There we are. So paper, you can see all the different paper ones. And then let me make sure unknown looks okay.
I have a question again.
Yeah.
So if you would be uploading, for example, CSV file, how the data inside of the file would look, or you need to have like again number of different. I have no idea. Explain, please.
It's a lot of time it's time series data is usually what I see, and so you'll have the rows are through time, if that makes sense. So like the first column might be a timestamp, and then the second column is like accelerometer X, and then accelerometer Y, and then accelerometer Z. And then so maybe you have something over the course of a second sampled at 100 hertz. So you have like 100 of these rows. And then so it's the XYZ over time. And so then you could plot
movement, for example.
Yeah. Correct. Yeah, you did like a movement, and then it would be XYZ over time, and then you could plot what that looks like.
Okay, perfect. I understand.
Sure. And then in Edge Impulse, I'm actually going to change this to 30 by 30. I find that if you try to go over like 32 by 32, the model is too big for this particular Arduino. So you have to use like very small images, which is why this Arduino is great for like real simple tasks. Keyword spotting is fine on. Image stuff really starts to tax it. So it only shows the image and raw data here. I'm just going to do image. I'm just going to convert to grayscale. That's all I'm doing. And then I'm going to use a basic classifier, which is a neural network here. So we'll save that impulse, blah, blah, which is what Edge Impulse calls this pipeline of this pre-processing. So right now it's just converting to grayscale. And all it's going to do is take all those images, which are already grayscale, because it assumes they're RGB, and it's going to create grayscale images and make sure they're all cropped to the right size, that 30 by 30. So while that's going, I'll mention that you were mentioning like, oh, this wand or maybe a keyword. Instead of this vision processing, you might have pre-processing that converts your one of the ways to think about like keyword spotting is I take my waveform over time. I use like a fast Fourier transform or something and make a spectrogram. Now that looks like an image. Most of the time, keyword spotting uses Mel frequency Cepstral coefficients, which is like a spectrogram, and then it goes through another discrete cosine transform, and it kind of creates these shapes, and then it does basically image classification on these shapes.
So it doesn't really compare the waveform, but you may compare different kind of calculations like spectrum, or maybe even more of them. Or
correct.
Only one of
them.
Yeah,
it's usually spectral. Okay. Most of the time, even like your wand thing, it's usually spectral, especially for like vibration analysis, which makes a lot more sense. But it does mean you have to do an FFT or multiple FFTs on top of your actual inference, so that more computational power is required. But that's where a lot of the DSP comes into play. Is you're doing DSP stuff on top of doing machine learning. But there are algorithms like these recurrent neural networks that work better with time series. I don't know how well they work on keyword spotting. I'm sure if somebody else has played with them, they could say something in the comments. But RNNs and like LSTMs, which are the long short-term memories, are a form of recurrent neural networks. Those supposedly work much better with time series. I just don't know how well they apply to keyword spotting, right? Doing audio data.
So basically, if you would be using this, let's say, Fourier transformation here in this learning process, you have to also then use it on the board when you will be converting the real data and accessing this model.
Yes. Okay. So anything you do here, you have to do on your board if you want it to work locally. That is very important to remember. So any transforms you do prior to that machine learning model, you have to, like, if you do an FFT, you got to do an FFT on your board. So, right. And sometimes I've seen it where like computing the FFT is more computationally expensive than the neural network, just because they are. So yeah, keep that in mind. And I'm going to bump this to 50 training cycles. They give you this is a neural network. So they give you one out of the box that actually works really well, and I'm just going to use it. So we were talking about hyperparameters earlier. I can add layers on top of here if I want to do different convolution layers, and I'm going to talk about those in a second. I can also modify the number of filters. I can modify, I could add like a dense neural network in here and add different nodes, add more layers. So you can modify it.
So these are the parameters what we were talking about at the beginning.
Correct, but these are what's known as hyperparameters. These are stuff that I can control. The actual parameters are the weights and biases inside the neural network that get automatically tuned, and I'll show you those in just a second. But if you're curious, this is all written in TensorFlow, so you can come in here and modify. If you know TensorFlow, you can come in here and modify the TensorFlow. So within Edge Impulse, yeah, if you know it, TensorFlow, go for it. So I'm going to start the training because it's going to probably take 5 minutes or so. And I'm going to go back to these. So I can talk a little bit about this idea of like parameters. What does it mean to be a neural network? So we're doing basic image classification, right? The classic one is cat versus dog. And the idea is I want to feed it an arbitrary image into this model, and it's going to tell me that it's a dog, or it's going to tell me it's a cat, right? We're going to do it with hand signals. So here's the real, like, what is a fundamental building block of a neural network is this thing called a node or a neuron, sometimes a perceptron. And you have your input. So that's the X's on the side, on the left side there, where you've got each X, in our case, is a pixel, is one value between 0 and 255. Sometimes you'll want to normalize it. A lot of times you'll see these be between a float between 0 and 1, but it's a number. It's just a number going in. Often each one of these is considered a dimension. So 30 by 30 is what, 900? So there would be 900 inputs to say a single node for us, if that makes sense.
Yeah.
Right. So there are 900 dimensions going in here. So then you've got these weights. And so each input is multiplied by an individual weight. So we've got a number here that's multiplied by a particular number here. So that's one of the weights. And it's a weighted sum. So all of these weights get added together. So you end up with this here. So we've got the individual values coming in. We've got the weights that multiply those individual values. They get multiplied together. And they also have what's known as a bias term. This gets added in as well. So you have our weight W0 gets added to each of the terms that have been multiplied by these individual weights. That's just a weighted sum. The thing that makes these work is this idea of an activation function. This performs some nonlinearity on this weighted sum. And when I say nonlinearity, I mean, you can't just pass it through. One of the early ones used this sigmoid function. So if this weighted sum was between minus infinity and infinity, this sigmoid function would basically compress that. So minus infinity would be an output of 0, and plus infinity would be an output of 1. And then so the sigmoid function would look like this. So you try to compress it between 0 and 1 to have an output. These days, we use something called the ReLU function, or the rectified linear unit. That just drops all your negatives. All your negatives become 0, and it just passes all the positives right through. It's real simple. This was created because computers can do this very easily, to just drop that sign bit. And the reason we need this activation function is because if we combine a bunch of nodes or neurons together in some arbitrary fashion, without that weighted function, or excuse me, without that activation function, a weighted sum of weighted sums is still just a linear weighted sum, right? It still becomes linear. And you end up with that problem we were talking about earlier, where you've got the groupings, and we would just be able to linearly divide them. That's all you can get with a linear function. But this activation function adds nonlinearity, which means now if we have groups in multiple dimensions, we can actually create divisions between them that are not linear. So that's why we need this activation function to do this. And so the idea is we can now combine these nodes. So each one of these little circles here is one of those nodes. And so all of our inputs, and I'm assuming, right, say accelerometer data, I'm not showing 900 dimensions here. Each of these gets fed into each of these nodes. So this first layer here, the input layer is often considered just your inputs. The next is that hidden layer, which is we don't see. That's not an input or not an output. And so each of these is one of those nodes I showed earlier, where it's a weighted sum of each of your inputs, and it goes through an activation function, and the output goes to the next layer, where we've got... Yes.
So if we are putting same data into this neuron, then is not output going to be same from each neuron?
So are you saying, like, if your x's are the same?
Yeah.
Yes,
so
it is
why do we need to have all these green dots and not only one of them? Because they should all then output the same number, no?
But they don't. So each node has its own set of weights.
Okay.
So each of those weights start to become a little different during training.
Oh, so initially they are basically same, but during training...
Yes. So initially you should randomize them. Usually between like 0 and 1 or -1 and 1, you should randomize these weights in all of your nodes. But during training, these weights, so like W1, W2, and WM, those become something else. So all of the weights and bias terms in this node are going to be different than the weights and biases in this node. And they're going to be different than this node.
That's interesting.
Yeah, and it all combines. And you can see how this gets more complicated. And this is like the world's simplest neural network right here. I mean, new ones have like millions of parameters and are hundreds of layers deep, and they've got like feedbacks, and they've got skip connections, and it's completely crazy. But this is the basic idea. So now each of these is looking for what the idea is, each of these nodes looks for a set of features. I'm going to call it features because you'll see later when we talk about convolutions what features might mean visually. And it's going to say, oh, based on the features, arbitrary features that I see, I'm going to weight certain things in each of these dimensions more heavily than others. I'm going to provide that weighted sum, and that gets fed into the next one. So then this node might say, I'm looking for different features, different patterns within here, and I'm going to feed those out. This one looks for a totally different set of patterns. So we have this pattern recognition machine that looks for different types of features and patterns and passes those to the next layer. So we end up with these arbitrary set of features that go down. And so we get into that problem of explainability, because visually, sure, I can kind of figure out which each of these features is looking at. But as we start going down the layers, I'm like, I don't know what these nodes are looking at. What are they finding? Until we finally get to this final layer where you often have one node per class in this output layer. And then it goes through this softmax function. And all the softmax function does is just say, I'm going to take the output of each of these and I'm going to combine them in such a way so that the probabilities across all my classes add up to 1. That's all it's doing. Because the output of these nodes is just saying, based on the features that I'm seeing from all the other inputs that I'm getting from the previous layers, I'm going to give you essentially a confidence score of like how strongly I think this belongs to this class. And the softmax says, great, now give that to me in probability scores. So now at the end of this, I have some arbitrary input, right? A picture of a dog this thing has never seen before. And it's going to say, right, it might be background, whatever it might be. I think this is a dog with probability 0.8. I think this is cat with probability 0.1, and I think this is the background, probability of 0.1, right? So that all adds up to 1, and based on that, I can say, dog is the highest, therefore, this neural network thinks that what I gave it was a dog. It belongs to dog class. Does that help?
I have 2 questions. So first one, if you would like to teach it, for example, hand gesture, then you have to do it all around the whole picture. It will not recognize like you have it in one place, and if you show it in different place, it will not recognize it, even if it.
So there's two ways to do that. One is I provide enough training where my hand gestures over here, and I have another set of training data where my hand gestures over here. And so what it's doing now is saying, I can identify hand gestures in these 2 spots, but nowhere else.
Okay.
Right. So it's figuring out where to look in the image to identify them. That's image classification. You could also do what's known as object detection. And that's where it says, based on somewhere in this image, I'm looking for hands, and I can give it training data to say, this is a hand, and it knows to look for hand in any position.
So you basically need to create small picture where only hand is and train it on the hand, and then you can find hand somewhere in bigger picture.
So usually what's preferable is to take pictures of the context, right? I'm standing in a camera and I'm going to give hand gestures over here, right? I'm going to take pictures in context, and then I go through in what's called bounding boxes. I go through and manually say, in this square is a hand. In this square is a hand. And that's the gesture that I'm making. And then that context helps the model figure out like, I'm looking at a background. It's not just one hand up in front of my camera, because then it's going to struggle to figure out what that means in context. And so right now I have different sizes of hands, and that's even better, right? I want to give it different sizes, different locations, different backgrounds. And now I can start to figure out where that means in context and start to look for those individual areas. But that bounding box is what you're saying. That bounding box is saying, this is a hand, right? I've got a little square drawn around here. This is a hand. You need to focus on this. This is what I care about. And then the model learns to do that.
Okay. So basically important is to say, if you just take picture like this, it doesn't mean it's going to work for whole camera.
Correct.
If you train it only here, it's not going to work everywhere. Or it can, but it's not so simple. There are other steps what need to be applied to be able to recognize it everywhere.
Correct. Generally speaking, the more data you can give it, the better model you're going to get. That's like a general rule in machine learning. The more data, the better. Always, if you have a problem with your model, the usual answer is go get more data.
Okay, so how does it work with dog and cat? Again, it will go through whole picture, find here is an animal, and then it will focus only on this small area and try to recognize only what is inside of this focus area.
Correct. So for our purposes, like dog, cat, or the hand gestures, I'm just saying like in this one area, like the image is mostly consisting of hand. That's Only look at that. That's
okay,
fine.
I understand.
Right. Real simple, real simple. Object detection's a little tougher if you wanted to find like a hand in different areas. But yeah, if you wanted to make like an actual like sign language recognition, yeah, you probably need to do object detection because it needs to look for wherever the hands are.
Okay, I understand. Now, second
Yeah.
question. So even when we start with different weights for these green dots, and if they see same picture, are these not going to end up with same weights at the end? Because they see same picture, no?
So wait, so you mean like during training, or do you
Yes,
mean
during
like
training, yeah.
sure. The weights are all randomized.
Initially,
So
yeah, you mentioned
initially,
initially.
yep.
And
So
then
initially they're
they will start correcting themselves based on the output or something, yeah?
correct. So I put up the overall training cycle here where you do a forward pass, right? You feed it a picture, it tries to just predict whatever based on the initial randomized weights. It's probably going to be wrong. We look at, we use a loss function. We try to figure out mathematically what's the distance between what I want it to be, the ground truth, and where it thinks it is, which is that predicted label. And then it goes backwards through the whole network and update the weights to try to make the output closer to that ground truth. So it tweaks the weights a little bit each time. And so then I feed it a new picture and it tweaks the weights again. And I feed it a new picture and it tweaks the weights, and it keeps doing that. Now that's stochastic gradient descent, specifically for neural networks, but you can also like batch process a whole bunch of images, collect all those differences between the input and output, use those differences to do like a batch update. That makes training a little more efficient, but it's not quite as accurate because one image at a time you can tweak as you go. So it's often a trade-off.
This weight number is going to be between 0 and any number. That's what was on the graph.
The weights can be anything. Most of the time you'll find that they're within like -1 to 1, give or take a little. Most of those algorithms, I think, try to keep them there, because if you have one that's super high, that means it's putting a lot of importance on that input, and then so that output of that node could spike pretty harshly if there was like certain features in there. I forget the exact algorithm thing that tries to keep those weights fairly compressed. Can't remember the name of it. Like what does that?
Okay, and then when it is adjusting the weight, how does it know if it needs to increase the importance or decrease?
That's the specific training algorithm. So during gradient descent, when it's looking at that loss, if I'm trying to remember this, so you can imagine that. So essentially, it's a plot of all of your weights, which can be X number of dimensions, with your loss function. So let's say you've got one weight. Yeah, let's say you have one weight and one loss function. So your weights would be like your X, your loss function's your Y. And then so you might end up with something like this, right? Like think like some valley. And the idea is you want to move your weight so that the loss function decreases, right? This goes back to like calculus 1 of how do you find a maximum or a minimum. And then so you use something called the gradient in order to figure out in an n-dimensional space, where can I move my weights such that it makes the loss function decrease, right? So you can think like a multi-dimensional space, and there's these peaks and valleys. I want to go towards those valleys. So it says, oh, if I tweak this weight and this weight and this weight, then I'm actually going to move a little bit toward down in that valley.
Okay, I understand now. So if it's only maybe I understand, I don't know.
It's calc and like linear algebra stuff.
So if it's only like two-dimensional space, let's say we have one input and one output, so and we know this loss or what is it?
Yeah, so don't think
difference
input
between
output.
what we want and what we have, then basically. So let's say on the input there is 1, but we are looking for 0. Yeah, it knows it's wrong, so it will change the weight, so it will become, the output will become 0 or something, and then we will know, okay, this is the correct one.
Right. And so if that's the case, you only have like one training sample, and you make it so that the output is 0, you win, right?
But this was the simplest example as we could.
Yes.
And then basically, if we have more inputs, then we are moving to different dimensions. So we are not looking only on like one graph or something, but we are looking on plane. Somewhere in the plane, somewhere in the space, there is this minimum which we need to find.
Right, right. So instead of thinking like the graph I'm trying to describe is instead of like inputs and outputs, it's your y-axis or z-axis or whatever is your loss function. That's the difference between your ground truth and your predicted label, right? Whatever that measure is, right? It could be some number. There's usually like very advanced loss functions because it affects how the training works. So it's usually some like crazy, I don't even remember like I don't remember like basic loss functions because they get out there as far as like how you compute that difference. But it's the difference between your ground truth and your predicted, and then your x or your n dimensions isn't your input variables now. It's your weights. It's the w's. All the w's. It's your entire training space. So when you look at that graph, and like maybe you could do a layer at a time, but when you look at that graph, you want to figure out how do I get to a valley, which is lowering L, your loss. But to do that, which way do I need to go to I update my W's in the nodes to move that L down.
Okay, I understand this. But then still, if you do it with second neuron and second cell and with same data, is not this space going to look same? Are not we going to look for same weights?
So say that again. If you're in the same L.
What I don't understand is how we can get different weights for this different neuron in same layer when we have same inputs. Because we are still looking for the lowest loss. We are still trying to tweak the weights. And theoretically, we should end up with same weights for all neurons, no?
For very, very simple ones, you do. And so imagine this. Imagine you're standing on that diagram I pictured. Imagine you have two weights. So you have W1 and W2. Like that's it. Let's imagine that. And then so now you have a loss function. And so almost always that loss function isn't like a nice gradual slope to a minimal loss somewhere. That loss function is actually peaks and valleys.
And each neuron will be looking for different valley in this loss.
Correct. And so when you initialize those weights randomly, it's the same thing as just like you're going to drop yourself onto that plane.
And I'm going to look for closest valley.
I'm going to look for the closest.
Okay.
And my learning algorithm, depending on how I set up my learning algorithm, it might say like, you might be able to do things like, I can get out of really shallow valleys and head towards deeper ones, right? I can start with very big learning rates and say, you know what, make big jumps. And then only when you get to big valleys do you actually stay in those big valleys. So yeah, it's peaks and valleys everywhere in 100-dimensional space. And so it's just very noisy. So you randomize yourself somewhere in there and you try to find in your region what is like a really good, like minimal loss, right?
I think I understand. Okay. I understand a little bit better than before.
Good. Yeah. I did. My favorite course that I took was Andrew Ng on Coursera. Goes into all the math behind this, and you have to do it like, I think he does it in Python now, but he did it in MATLAB when I took it. And you have to like do all of this manually. And so a lot of this was like a few years ago. And a lot of this I have like, I've forgotten, like, how do you compute an exact loss function? I'm like, I don't remember. But those general concepts stay around. And he does a really good job of explaining all this.
Okay. Thank you for this explanation, because I never knew exactly how. I'm sure I still don't understand exactly how it works, but at least I can imagine it a little bit better. Okay, we can move.
Sounds good. So real quick, when we get to the end of that training, it's probably done by now, but we'll see something called a confusion matrix. And this is, you'll see actual labels on one side, predicted labels on the other. Usually this is done to like a validation or a test set, so you can see how well your model is performing. And you can use this to calculate all sorts of metrics. But we often care about the accuracy of how well the actual label matched up with the predicted label. And you can see this for your training set, your validation, and your testing. So I'll leave it at that for now. But I'm going to throw a curveball because we're not using dense neural networks. You're using convolutional neural networks.
So I have no idea what's different, but I'm going to find out.
Yeah. So the idea behind a convolutional neural network is instead of doing the weighted sum with some activation function, with like all of our inputs, we're going to perform what's known as convolution, where we take some sub area of our image, in this case, a 3x3, we're going to do a weighted sum with something called a kernel. So these are your weights now in this kernel. So the 3x3 area sub image, we're going to multiply to a weighted sum with that kernel, and that's going to output. So all those is 64 in this, I'm going to call it a new image. And then so the same thing, we move that little window over, the kernel weights stay the same this time, and we're going to do the same thing. So now we just keep moving that sliding box over. You notice the kernel keeps staying the same, and we're going to have that weighted sum. When we talk about neural networks, convolutional neural networks, this does go through an activation function. So these would go through like your ReLU or your, oh goodness, keep wanting to say softmax, but it's the sigmoid function. So these would go through that nonlinearity, but this is the basic idea behind convolution. So prior to convolutional neural networks, we would use convolution to do things, a lot of things in computer vision, for doing things like edge detection, blurring, sharpening. They're very useful even outside of machine learning. So here's an image of an elephant. These are different kernels where I've done the convolution operation, and you can see based on the weights of those kernels, I can create a blur, I can create a sharpen, I can do edge detection. That's what we're using for convolutional neural networks. Now, when these become the weights, these become our weights that are automatically updated. And what we find is that when we do it in a convolutional neural network and we run it through the training algorithm, these weights start to, even if we randomize these weights, they will start to tend towards things like edge detection, because it starts to figure out, oh, if I want to identify elephant, what I care about are the location of these edges. And so you will see, like, it created an edge detector, which is super wild, that like it will just randomly tends towards edge detectors. So that's what we're doing with convolution, is trying to extract meaning from these images.
Okay. So
sure.
Go a little bit back. One slide back. Yeah. So basically, we are creating kind of another image which we will then analyze, or?
Yes. So we keep doing layers of these convolutions, and so the idea of these new images that we're creating is we're extracting features from that original.
Mm-hmm.
So one might be blurred version,
Mm-hmm.
one might be left edges, one might be top and bottom edges, and so we start creating these new images that are features from the original.
And where we put these other images?
Wait, what's that?
Where we are going to put these other images, or how we are going to use them?
We don't. These are just stored in memory.
Okay. So why do we need them?
Because it creates that feature. Remember how we were talking about, like, with the voice, right? We do a fast Fourier transform and we get that, and then that goes to the
okay.
The
so basically, this way you will find the best image which we can use as input for the model.
Yes, okay. This becomes that fast Fourier transform or spectrogram that we were using previously. Now we've just stacked this pipeline on top of our classifier, which is a dense neural network. We've put this on top of it and said, you know what? You're now one model. And the first part of this is going to say, you're going to extract features for me, and you're going to figure out what features you need to make the best decisions. So we're just saying, learn whatever features you need. We're not going to tell you what features, you're going to learn it.
Oh, okay. So you basically provide, or there are a number of these features like the edge detection or blur or something like this. And we need to select the one which is the best for what we need. And
correct.
This is part of the learning process, or it is inside of the machine learning model?
Both. It's inside the machine learning model, and it's also part of the learning process.
Okay.
So the weights, if you think about, remember how I said those individual nodes, based on the weights that are going into those nodes, those weights can say, oh, these are really important features. So from these filters that I've created, it might say, you know what, left and right edges are super important, but that blurred image is not very important. So the learning algorithm can go, you know what, try something new, update your features, your kernel. So instead of doing more blur, find me more edges, because that's what my classifier has determined is the most interesting parts.
So okay, I'm still a little bit confused. So
So
we take the
I'll
raw
give you an
data,
image.
raw data from the image.
Sure.
And then we apply this filter, and then we fill this data from the filter to learn our model.
Correct.
Or
so I'm gonna skip ahead here to show you how this
okay.
works. So an image, yes.
Okay.
So this is your feature extraction. I might do multiple convolutions. There's this pooling layer, which I can show you in a second. That's actually just picking the highest value pixel out of a group of pixels. And then so where we started with this, my 30 by 30 or 28 by 20, whatever image, it's going to go through these convolution layers. And where I say convolution, this is not one convolution. This actually might be 5 convolutions that happen in parallel, right? So that first layer might be an outline, a top and bottom edge detection or Sobel, and then it might be a sharpened image, right? It might be several of these convolutions that get fed down, and then those get fed into others. And this is like the simplest convolutional neural network. You can see where it gets really hard to wrap your head around what's going on inside of these things as they get obnoxiously complex beyond this.
I'm still thinking so basically the weight is basically doing this. Changing the weight is doing the blurring or edge detection or
yes, exactly. So in addition to our classifier, so these are those nodes I showed you earlier. This is a dense neural network, or one layer of a dense neural network that does the simple classifier.
Okay. I understand.
Right.
The last one, I understand the last one.
So you got that part. So instead of just flattening out all of the pixels and sending those to a dense neural network, we're going to do convolution. And then so the weights in each of these convolutions, so this one convolutional layer might be several convolution operations. And so you might get something like this. But these parameters in the kernel are automatically updated. So I think that was the question you were asking, right? We don't set those.
Oh. Okay, I'm lost. Okay. So where you say flatten to vector, it means that's the real machine learning? Flatten to vector?
Right. Technically, all this is machine learning. Technically, it's like, even though this is the feature extraction, because we're updating those weights automatically to help the whole process, this is now part of the machine learning process, and this whole thing is the model. But this part is feature extraction. This part is a classifier.
But what I still don't understand is how these weight numbers are correlated to this special filter what we are using. How does it, or we set up these weight numbers based on the filter what we would like to use, the initial numbers, or that's what I don't understand.
So how are these numbers updated?
I think I'm lost. I really don't understand this.
I lost your convolution. Oh shoot.
And I thought I will understand.
No, it's. I mean, I'll show you at the end, but I've got a whole course on doing this stuff, and I cover all this in a lot more detail than the time we have here. But yeah, I have students do this by hand, so you can wrap your head around what's going on in convolution.
Okay.
So all the convolution is doing is just you take the subset, you multiply it by this kernel, right? It's just a weighted sum. So you can treat these like your weights in the nodes that we saw earlier. And then it outputs into this new image. And then based on what you've set in this kernel, that's how you end up with all these new images.
Okay, so from this you create the weights, but you still apply the raw data with the weights together.
Yes. It's still just the raw data coming in. It's a weighted sum, but rather than weighted sum across your entire image, it's just these little subsections that's a sliding window.
Okay, let's stop.
Okay, we're good.
Let's move.
So, we can keep moving here. But the idea is by the time this feature extraction goes, so this first layer might be things like edges and certain shapes and things that get picked out. And then the deeper you go into these convolutions, it might be oh, it's a general concept of an eye or a nose or an ear. And then those go into this classifier. There's those features that say, oh, I see two eyes kind of in this location. I see an ear here and a snout that's like a ways away. That's a dog. So it then gives you that classification based on those larger features. So in addition to extracting those features, we're also shrinking the size of the input going into our classifier.
Okay.
And it allows it to look at different parts of the images rather than saying these 3 pixels must be an eye. Which is a problem if you just use a dense neural network rather than this convolution.
Okay. I think what I learned from this is it's not so simple like I'm putting data here and this is the output, but I work with this data and trying to have a different view on this data to find the best one which will help me to recognize, oh, okay, this is eye, because now I can see the shape of the eye in this whole picture.
Right.
That's what is important, because originally I thought it somehow only scans through all the pixels, and based on these pixels it will say like, okay, this is a dog, but that's not true. It does something with the picture. It tries to redraw it to, I don't know, see the edges or something,
right,
and then it detects from this. Okay.
Yes. Yeah, that is exactly what's going on. It's looking for these features in the image rather than, so like if you tried to do like the same thing with like a decision tree, that would be like, oh, is this first pixel above this value? Yes or no? What's the next
that's what
pixel,
I was thinking,
right?
like
that's like classic machine learning decision trees, and you know, there would be some learning in there as far as like, oh, what are the values that my thresholds are set? But that's exactly what's going on in like old school classical machine learning. But yeah, like the new stuff is like completely bonkers.
Okay, because this is much more efficient. I'm pretty sure you don't have to look for everything. Just find the contours, and just the contours will help a lot, I guess.
Yeah, and it's not just like classic computer vision. This feature extraction area would be manually done. It would be, oh, I know that edge detection is good, so let me get some edge detectors in there plus some blob detectors, and now I'm going to send that to whatever my classifier is. Like it might be a support vector machine. So that was kind of your classical, how you would set up a classical computer vision with some machine learning, right? It wouldn't be neural networks automatically learning this stuff. The idea is, oh, instead of a human going, let me design these edge detectors and whatnot, it's just let the machine figure it out. It's like kind of you throw a sledgehammer and just be like, let it figure out what it needs.
And we need to have it inside of the model, because then when we would like to use it, for example, on a microcontroller, we really don't want to do edge detection on the microcontroller. We would like to feed it with raw data and leave the model to decide or find these edges and then decide what is it.
I mean, it might be doing edge detection, right? Some of the convolutional filters that we set up might be edge detectors, and a lot of times they are.
So you have to also run these filters on the microcontroller on the raw data. Okay.
Yes. So I'm gonna go back to oh shoot.
I'm very slow.
No, you're good. If you haven't seen this stuff before, it can be completely bonkers as to what's going on. So the entire model consists of my convolutional and pooling layers. And there's 2 layers. It's pretty much that exact diagram I just showed you. So these are my filters. These are like, this could be an edge detector. This could be a blob detector, whatever those filters learn to be. But it is a little bit of a sledgehammer in the sense of, I'm not going to meticulously craft these filters, right? I literally just like pushed a button. I said, start training.
Okay.
Waited some time, and it figured out what filters it needed to identify these features.
Okay, so what do we see here?
It's okay. My validation data is a little above 90%, which is not bad. In that workshop, that GitHub link I posted, there's a thing where I do data augmentation. So you take 50-ish pictures of each of the hand symbols, and then it does data augmentation where it like zooms in, zooms out, moves them, rotates, crops, adds noise in, and you go from like, what is it? Is it 5 classes times 50? So you go from like 250 images to like 3,000 images, and you can get this up to like 95%. It works much better. But I wanted to skip all of that right now for the sake of brevity, and we can focus on like how this is working. But if you work through that, if you decide to go through that, it's all open source. Have fun with it. Definitely give that a shot, and because you'll see how data augmentation can really help your accuracy. So what I like to do from here is always test. So the model has never seen this data before. I fully expect the model to be a little overfit, which means it's going to perform worse on these new images.
Okay, so basically when we set up the 20-80%, it removed the 20% out, it learned itself on the 80% of the data, and these are the 20% which are unknown for, which were not used for training. So it's just trying to figure out if it's right or not. Do we need to check it manually then, or it will check it?
No, it's checking it for me. Like, this is just a tool that's set up, but right, like you're saying, it's also known as the holdout set, either like a set aside or a holdout set. I don't even know if I made set aside up. I'm holdout set or your test set, right? The model never sees it. This is just push button and get it. But like in TensorFlow, if I was doing this, I would have all that data set aside, and then I would just read that in and call. There's usually like a .predict function, or just run it through my model, tally up how often it matches the label, and then I can calculate my accuracy from there. So as you can see, my model's actually overfit. It overfits that original data, so it's performing worse on this holdout set. I fully expected this to happen. 76 is enough that when I deploy this, it's gonna kind of work if I hold my hand in the right position. But what I found is when you do data augmentation, this bumps up and it gets less overfit because now I have more robust data to teach the model what to expect. So from here, I'm going to deploy as Arduino library. Int H is fine. Yeah, we didn't even touch like quantization. So like, how do you take that machine learning model, which is usually working in floating point, right? It's all calculated in floating point. And then how do we quantize that so it works more efficiently when you don't have something like a floating point unit on your microcontroller? So it usually takes up less memory. It's faster, especially if you don't have a floating point unit. But you usually lose a little bit of accuracy because of that quantization error. If you've ever worked with like DSP stuff, you know that quantization can be an issue sometimes.
So basically, we created some kind of library which is specific for our microcontroller.
Correct. So all that it does is it takes that model, which is just stored in TensorFlow. It's all those weights and biases and how they're connected. And then it wraps it up into a C++ library. And Edge Impulse is nice because it then like takes that and like makes an Arduino library over it. I believe TensorFlow Lite Micro has some Arduino options for it, but this is just much easier to use, and you can like watch me push buttons rather than like go through like hundreds of lines of code. And so it's just wrapping that whole thing up in a Arduino library, and we're just going to import that. And then all we have to do is feed it data, and it spits answers out for us.
Okay.
So now we've got this like funnel that we can just, it's a library.
I have one question. If someone is worried if they have to use this Edge Impulse, theoretically, you can take this model from Edge Impulse and use it with different kind of system once. Because what I knew about Edge Impulse before, but originally I wanted to make a video with something what is not commercial, because for example, when I train something and I have to create, I don't know, thousands of data, I really don't want to be locked with one system. So that was my worry. So if you train something, can you somehow get this model out of this system?
Sure. So when you go to deploy, in addition to Arduino, you see the other ones here. So like C++, you can get it as a C++ library that's actually wrapped around TensorFlow Lite Micro. So it just kind of wraps some of those calls up nicely. And then if you have one of those like spectrogram or feature extractors that you've created, that like is slapped on the front of it. So it makes that pipeline a lot nicer. But you can also go here and you can actually get your TensorFlow. Here's the full TensorFlow. Here's the full Keras model. It doesn't have any of those feature extractors, not the CNNs, but I mean like instead of image, if we had like spectrogram here, right? You did something manually. It wouldn't have that, but your model can be exported as a Keras.
So you can download it and you can use TensorFlow instead of Edge Impulse, correct?
Correct. And I've done it both ways. I've done like the full training cycles in TensorFlow and then spit out TensorFlow Micro. You end up in like version hell pretty quickly. and it's actually pretty rough to use. So especially like teaching, I like to use Edge Impulse just because like it's visually nicer. But yeah, you can easily get all the stuff you've created in here out.
Is it
The only thing that's
expensive? I'm Edge
what's
Impulse.
that?
Edge Impulse, is it expensive?
It's for developers, it's free up to like 20 minutes of training time. I teach all of my courses. The professors I've talked to, every now and then I run into students who need like a little extra training time. So usually it's like, hey, if you like make your project public and open source it, then you know that helps us because like we generate content. Be like, oh, you can use this person's project and we'll give you extra training time. There's like enterprise features where it's like, oh, I've got this like data store from an S3 bucket, and I can transform my data to come into several different machine learning projects, and I can set up like triggers so it does it automatically. That's where our like enterprise license comes in. But for just doing the stuff that I'm showing you, it's all free.
Okay, okay, we can continue.
Sure. So now that we have
We have
that
the
stuff,
Arduino library, correct?
yes.
So I
Oh,
guess we
software
need
update.
to go back to GitHub and use the second step, maybe.
Correct. So I've
Okay.
got, so this is the repo's here. So I've already obviously cloned the repo. So I'm going to skip these. I'm going to go right to live inference.
Oh,
And I
so
will,
we don't need to do anything else?
no, that's it. I need to, one second. I got to move my little window out of the way here so I can see what I'm doing. But I'm going to go into Arduino IDE. I'm going to go to Sketch. I'm going to include my library as a .zip. And wherever my downloads are, here it is, EIRPS. So that's the one I just downloaded. That's the model I just trained. So I'm going to include that. It's going to take a moment because these libraries are actually pretty big. There's a lot going on in that C++. So we've got it installed. And then this is my serial image capture, which I don't want. I want my live inference, which is a little different. I don't care to save those images, and then it needs to call that classifier. So let me start compiling because that also takes a few minutes.
Okay.
And I'll kind of, I'll show you a bit of the code, as soon as Arduino stops.
And what is in the steps
thinking.
2, 3, and 4, which we skipped?
So one of them is the data augmentation step, and that's not an Arduino library. That's actually a Jupyter notebook. It's a collab. That shows you how to like do all those transforms so you can create a robust data set. The next one is doing static inference, where you take a known good image, you feed it through that classifier, and you compare it to the answer you get, say, on Edge Impulse or your TensorFlow library. I always do that prior to writing live inference to check that my classifier is working the way I intended. DSP, you would do something similar, right? Like, oh, I use MATLAB or Python and I created my DSP function, right? I created my filter. Great. I'm going to rewrite my filter in C or C++, and then I'm going to give it a known good input and make sure it matches the output with my high level language. Same idea. And then I need to change. Oh, it did not open correctly. This is still that one. Okay, thank you, Arduino. Oops. I want live inference. Open live inference. There we go. So different sketch than what I was showing you originally. So instead of, I'm going to call this RPS because that is the name of the library that I just downloaded and installed. I'm going to start, let me make sure I can see my Arduino. Yes. And I'm going to start that upload process while we kind of look through what's going on here. So I'm going to set it up just like the images we captured. It's going to be that 30 by 30, right? Anything you've captured as your input for training, you should be using the same thing when you deploy live for inference. These are just kind of I did some functions to kind of convert stuff to grayscale for me. But what we care about, yeah, here it is, like crop center. This is just manipulating that image when we capture it. So we're going to crop and scale it to that 30 by 30. Edge Impulse expects RGB 888. So this is actually this 565 to 888 is probably not needed. I think I use that when I export out, or sorry, I transmit over USB so you can see the image in that Python script. This is the one I care about. I'm going to convert grayscale to 888, and all that's doing is just copying those values to each of those channels. It's a little inefficient, but it allows me to work with that Edge Impulse library. This is for spitting out over USB. Set up the camera. I'm going to capture it. So this is my loop function. If you're familiar with Arduino, I'm going to create a new capture buffer. It's going to read it in. So there's where I read it from the camera. It's going to scale the image somewhere. It crops to that center, so I get that nice 30 by 30 little square. Convert image for the correct format. I'm going to convert grayscale to that RGB 888. And then here's the magic function where I pass it that signal, which is my buffer. And I'm going to drop the results into this variable right here. So this is that edge impulse function called run classifier. And that just sends my raw image to the edge impulse stuff. It performs inference using, did I click the E on? Yeah, it's actually compiled C++ code. It's actually compressed. It's not using TensorFlow Lite. Yeah. And then it's going to print my results. And then, if you want to challenge, turn on one of the LEDs based on the hand symbol you're seeing. And that's it. It like frees up the buffers after that.
So what is the output which you will get from the library?
So that is I believe it's a struct. So it's dumped into this thing called result. Where is it? Yep. So it's dumped into this struct called result. And then in that struct, there's a whole bunch of stuff. So like I can get timing, so how long it took to do each of the things. And what you care about most is right here, result, classification, the class. So I've got class 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4. And those line up with underscore background, underscore unknown, paper, rock, scissors. So it's alphabetical order. And then so I just print those out. So I'm also printing out the categories, so the class labels. And then that value is between 0 and 1, and it's the probability that the model thinks that the class belongs to that input data.
And where you can find all this information? Is it somewhere on your website?
Yes.
Like more description, how to use this library.
So in docs.edgeimpulse, API reference. I actually wrote this.
You wrote this?
Well, not all of this. I wrote this section, the C++ inference SDK library. So under here, it's a little description. So the inferencing library, it's the same as the Arduino library, right? It's just calling C++ functions. And then so if you go under functions, you can find run classifier. So this gives you an example. This shows you what your parameters, your returns are, and then even gives you an example of like how to use that. So there's run classifier continuous, which kind of saves some of your features. You need to call init, but I think before using continuous. And then how to use some of the structs. So like here's what that output of that result is. So here's all your members inside of that struct. Does that help?
Yeah, that's what I was looking for. Okay.
Sweet. All right, let's see if it is finished compiling. Yes. All right, now I always check my output. Okay, so we are getting stuff. We're getting prediction results. That is a plus.
So what
now?
Okay.
Give me a second here. We're gonna have a moment of truth to see if the Python thing works for us, because now you can see my hand over it, and I'm gonna switch my camera again.
I'm curious.
Meeting, switch cameras. Okay, here we go. So you see my hand. So now we have our moment of truth, whether this is gonna work or not. All right, so we have the little image. Yes, this looks good. So we have what the camera sees up here, right? And then down below, it's spitting out, what was it, like 2 frames a second, or it should show us, 2.5 frames a second. It's spitting out the inference results. So right now, it thinks it's background. So, right, it's not great. It is whatever the highest value of these are. So it thinks it's background with 0.7, probability 0.7. 70%, it's like, I think this is a background. And then it thinks it's unknown with 0.14, and then the others like, around 0.01 or 0.02.
Okay.
So I'm going to put my hand over this, and it doesn't know what to do with that. So it's going to classify that as unknown. So it's the highest, right? So 0.7 something. I'm going to give it rock. Let's see if it knows what to do with that. Sure enough,
cool.
0.9, 0.8. Yep. And then let's try scissors. Lower, but not bad, 0.5. It's like, it's one of those, if my hands are in the exact right position, it's gonna find it. So maybe bring it up a little bit. What is it thinking? It's kind of unknown. It's kind of unsure what to do with my hand. There it goes. Anything over like 0.5, it's 0.7. There it goes. So scissors, and then we'll try paper. And then sure enough, paper is 0.9 down here. And then with these numbers, you can obviously do something like, say, put simple thresholds in there. And so I've got a quick diagram to kind of show what that might look like. So here's what we're doing, right? We've captured from camera, we pre-process it to like convert to grayscale and crop, we send it to the model, and the model gives me the probability that it thinks belongs to those. So the idea of a threshold is now I can say, oh, I want to identify rock. So I might set a threshold of if the probability of rock is over some threshold, like 0.5, then do something with that information. Light up a light, tell the Internet of Things database that you gave it the rock symbol. The issue is it doesn't often look like that. It looks something like this. So you end up with true positives and true negatives. So what you really want to do is slide that threshold to an area. So in this case, if you made that threshold higher, like 0.7, it might miss some rock symbols, but it would also not give you as many, say, false negatives, if that makes sense.
So basically, these numbers are always from 0 to 1 for each item. So it's not like in total 100%, but each one is from 0 to 1.
Because of that softmax function, they should all add up to 1.
Okay.
So if I bring that back up again, so if you look at these, if you add these up,
okay.
So it's like 0.7, 0.1,
So from
0.1,
this, you should always know
0.9.
which one is which one has the highest probability.
Yes, you can always figure out which one has the max.
Yes.
But it's always a good idea to set a threshold to say, if you think it's a rock with 0.4, it might not be. It's not very confident that that's rock.
Okay.
So you often want to set thresholds based on what your targets are.
Okay.
And then same idea, right? You could lower that threshold. You could say, oh yeah, anything with 0.3 or above, make a rock, or whatever the highest is, as long as that's above 0.3, then that's the class I think it is. So you could either find the max, or you could set threshold, or you could do both.
Okay. And we are finished, no?
Yes, yeah. This was everything. So come on, Python. There we go. So yeah, you have like. Scissors was the toughest one. It actually struggled a lot on scissors. But in the exact right position, and this is where like data augmentation can help. Right, it helps me create a more robust classifier, like a very specific distance away. Oh, there it goes, 0.7. Yeah. I need more data, obviously, to make it help here, but it is working. It absolutely is working. And it's all being, and to answer your, I think, question, like way back at the beginning, all the processing is being done here. Not like the only reason I'm sending information to my computer is so that you can see it on this image cap. And like, I want to see the results and see it here, but I could unplug this. I could do like change the color of the LED based on like the, rock, paper, scissors I'm giving, and then just plug it into some power and it would absolutely work. Like all the machine learning is being done on this device.
Cool. You can switch back your camera. So I
Sounds
have
good.
a few more questions. We only have like not
We're probably
not
way
much
over
left.
time.
I don't want to make it longer than 2 hours.
That's fair. Can I give a shout out to like courses and books if anybody really wants to dig into this stuff? Sweet.
Put back your camera.
Okay.
So everyone can see you. Also, before you do the shout out, so if someone would like to try this, they will need to buy the hardware, and then they go to your GitHub, the one which we were using, and there are all the steps described how to do it.
Yes. So this shows you which hardware you need, and you can follow all these steps.
Okay.
And it will walk through exactly what I just showed. And there's actually in here, there's also like the slides if you want to see some of the information. So those slides I showed you, a lot of them were just taking pieces from here to make this fit within 2 hours, because this is usually like a 4-hour workshop.
Okay. Now you can say what you would like to say.
So if you want to really dig into this stuff, I recommend, so I've got a course on Coursera. I've got 2. One's Introduction to Embedded Machine Learning. That's where you would want to start. The next one is Computer Vision with Embedded Machine Learning, and that's kind of the follow-on that gets into some of the stuff we were doing here.
Show it. I'm curious.
Sure. So here's Introduction to Embedded Machine Learning. Here's the syllabus. So the introduction, we go through some neural networks. I've got a guest lecturer who's a professor. He comes in and he gives a great introduction to neural networks. And then we actually get into that keyword spotting where you create a whole system using this information. And then the next one was the follow-on course was computer vision. So here's computer vision with embedded machine learning. Something similar. We go through we give a review of neural networks, kind of how you can use neural networks to identify, classify basic images by doing that flattening operation. And then we get into what does it mean to do convolutional neural networks, which is exactly what we saw here. And then we talk a little bit about object detection at the end, which is what you were asking about, Robert. We're like, how do you identify where your hand is in the image and classify what that is?
Cool.
Yeah, and then I also highly recommend Professor Reddy from Harvard teaches this course on edX that is it goes into a lot more depth where mine's kind of like an overview. We play with this, we touch a little bit on the theory. He's got you digging into TensorFlow and doing the like operations kind of yourself. So it's a lot longer, more in-depth course, probably closer to like a full college course. He does teach a college course at Harvard, a graduate level course, and it's very similar to what you would find in that. And then of course we've got books, the TinyML book. That was kind of like the start of all this with Pete Warren and Dan Sitaniaki, who created TensorFlow like micro, and they like really dive into the details of all of this. Then there's that high level AI at the edge, and then the TinyML cookbook that just gives you a bunch of projects you can do, which is a lot of fun.
I like it. I really enjoyed creating this video because you would not believe there are so many people who say they know how machine learning works and they know how to go and repeat the tutorials which are on internet, but actually there are only few people who really understand what is really happening. So thank you so much, Shawn, for explaining all this.
You're welcome. Anytime. I'm really happy to share, and this stuff, obviously gets me very excited. It's so cool. I think it's like a leading edge of what we can do with embedded systems. It feels a lot like, not that I was around for the 80s or remember it, but my understanding is this is kind of like what the 80s saw with the advent of like digital signal processing, and now we have all this new hardware and all this development around it, and just new things we can do with embedded systems. I think it's so cool.
So thank you so much.
Yeah, thanks for having me on. This was fun.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.